Hello, everyone, and welcome to the second in our Quantum Women Invited Talk series, where we highlight awesome and accomplished women in the industry to inspire the next generation of quantum researchers and developers. My name is Radha Pyari Sandhir. I'm the India Community Lead at IBM Quantum and your host for today. Thank you to each one of you for tuning in today. And as always, the chat box is open for you to use. Please feel free to drop a hello or tell us where you're tuning in from. And with me, I have a very special guest who I will introduce shortly. Hello, everyone. I see the chat lighting up. Um, After her talk, we will have a Q&A session for about 10 minutes or so, where you will be able to drop your questions in the chat box. So if you do have a question, please save it for towards the end, because if you type it sooner, we may miss it. All right, now. Dr. Özlem Salehi is a postdoctoral researcher at the Institute of Theoretical and Applied Informatics of the Polish Academy of Sciences. She obtained her PhD degree in the field of theoretical computer science in 2019 from Boğaziçi University, Istanbul, Turkey. Her research area focuses on quantum optimization. In particular, she has been recently working on modeling and solving combinatorial optimization problems using quantum annealing and QAOA. She is one of the coordinators of the Q Education Department under Q World, a nonprofit organization active in 24 countries and popularizing quantum technologies. She has organized and instructed quantum programming workshops and developed open source educational materials to promote quantum computing. So it is my great pleasure to welcome Dr. Salehi to the stage.
Thank you very much for the invitation and also for the nice introduction. Let me share my screen. Just a second. I will share it soon. Okay. I guess you can see it right now.
All good.
Thank you again for the invitation. This is Özlem. The first part of my talk will be about my background, how I ended up in this field. It will be about QWorld. And the second part of my talk, I will focus more on my research activities that I have been doing recently. So let's start. As Radha mentioned, I have a bachelor's degree in mathematics from Boğaziçi University, Turkey. I'm from Turkey. And then I studied computer engineering during my master's and PhD studies, again in Boğaziçi University. And during my PhD, I focused on theoretical computer science, in particular automata theory. So I did not have any background on quantum computing other than a graduate course I took on quantum algorithms back then. I worked as a teaching assistant for 8 years at Boğaziçi University at the Department of Mathematics and Computer Engineering. On the right-hand side, you can see a photo of mine, which was taken on the last day of my teaching assistantship. Then I started working at Özlem University as an instructor in computer science department. And since 2021, I am working as a postdoctoral researcher at Institute of Theoretical and Applied Informatics of Polish Academy of Sciences in Poland. Actually, I'm working remotely. I'm in Turkey, but I'm working remotely in Poland. And it was in 2019 when I entered into this field of quantum computing. So let me briefly mention how this happens. In May 2019, I heard that there would be a quantum programming workshop in Ankara, in Turkey. And one of the co-organizers was Abuzaya Kayılmaz from University of Latvia. And he is one of the former students of my PhD advisor, Cemsay. And this is how I heard about this event. And I thought, okay, this can be interesting. I had no idea about quantum programming back then. I just had some ideas about quantum computing, but it was just due to a course I had taken. So I went there, and you can see me on the left. I joined this quantum programming workshop, which lasted for 3 days. And one of the co-organizers of this workshop was Zeki from Ankara, Turkey. And at the end of this workshop, we thought that we should organize more workshops like this. The material was really great. It was introducing quantum computing through quantum programming, and it was requiring no physics, and it was great for someone like me who had background on maths and computer science, but no physics. And there we also initiated Q Turkey, which is a non-legal organization, a gathering for people who are interested in quantum computing in Turkey. But back then, actually, I was looking for something to switch my research topic. So I was studying automata theory, and it was the end of my PhD, and I was looking for something new. And I thought, okay, this can be the new thing I should study. And like after 3 months, we organized another workshop in Turkey. And then I was instructor at this workshop. Like since I had some teaching experience, I studied the materials, etc. And then, okay, I became the instructor for the workshop. And on the right, you can see me instructing during the workshop. So this was how we established Q Turkey, together with Zeki and other people who joined that workshop, either as participants or as mentors. And since 2019, I am one of the coordinators of Q Turkey, and we are organizing quantum programming workshops, we are organizing webinars, we are organizing hackathons. We have reached thousands of people in Turkey, and we are the first such community in Turkey, which is trying to popularize quantum technologies, quantum computing, and trying to gather people together. And so this is Q Turkey, but in this picture, you can also see some other cities. What Abuzay and his team did was to travel through those cities, mostly in Eastern Europe, by a car. And this is why the name of the project is Q Drive. During the summer, they traveled by a car to those cities, and they organized their quantum programming workshops, which we name as Q Bronze, Introduction to Quantum Programming Workshop. And at the end of the summer, Q World was established. And like Q Turkey, there were local communities, Q Poland, Q Hungary, which we call Q Cousins. And Q World is a non-profit organization which is trying to popularize quantum technologies since 2019. And currently, Q World is active in 24 countries. So we have 24 Q Cousins, and over 100 programming workshops have been organized in different levels, and over 4,000 diplomas were handed out during those workshops. And all of this is done voluntarily. As I mentioned, it's a non-profit organization. And under Q World, there are some departments, and I am one of the coordinators of Q Education Department. And as the Q Education Department, Our main responsibility is preparing education materials and organizing global workshops. For instance, QBronze is our introductory workshop. This was prepared by Abuzaya Kayılmaz, as I mentioned, and in this material, there are no complex numbers to ease the complexity, and there is no physics, so it's prepared through a computer science view, where you start with classical systems, then you have probabilistic, and then you have quantum systems. We even have an article about this, published in IEEE Transactions on Education, about effectiveness of this method for introducing quantum computing to people with different backgrounds. For those who are not familiar with Python and linear algebra, we have QPrep. And once you complete QBronze, you can continue with nickel or silver. In nickel, we have those conventional quantum algorithms like Deutsch-Souza, and we have an application of Grover's algorithm. By the way, QBronze covers everything like entanglement, superdense coding, quantum teleportation, and even Grover's search. And in silver, we introduce now complex numbers, gates with complex numbers, block sphere, and quantum Fourier transform, phase estimation, all the way up to Shor's algorithm. QBronze is using Qiskit, and we even have a Qiskit version, QBronze Qiskit, which is certified by Qiskit. And nickel and silver, they are using both Qiskit and Circ programming framework. And all those materials are open source and available in QBronze website. Time to time, we organize global workshops, but mostly we have local communities organizing their own local workshops. Sorry. And besides those workshops, last year we organized a summer school, which contained lectures on bronze and silver, also some quantum programming sessions, networking events, some webinars. It was for 2 weeks. And since last year, we started Q course. This is a 1-semester graduate course, which is free for registration for everyone who is studying a graduate degree. You can check more about those in our webpage. Apart from Q Education, there is a Q Research department under Q World, and the main aim there is research activities. And one of the most successful events organized by Q Research department is Q Intern, which is organized during summers. Professors from all over the world propose some research projects, and the interns who are interested apply for those projects, and they can work together with the professors on those projects. And we have quantum science days, we have some webinars on web. You can check our webpage for more detail. Now, this was about my background, how I ended up here, about QWorld. Now I would like to talk about my research activities since I started my postdoctoral researcher position. So my main focus is optimization problems and how to solve them using quantum computing in the NISQ era. And for this, there are 2 main approaches I have been considering, and those are the 2 popular approaches. Let's start with the first one, which is quantum annealing. To talk about quantum annealing, we should first talk about adiabatic quantum computing. This is an alternative computing framework. Probably you are familiar with gate-based computers, where you have some qubits and you are applying some gates. So the computation is discretized in that sense, but AQC is different. And this is relying on quantum adiabatic theorem. And let's see what this theorem is stating. Suppose that you have a quantum system, and suppose that initially this quantum system is in its ground state, meaning in its lowest energy state. Then suppose that you are evolving this system through a time-dependent Hamiltonian, meaning that how you evolve the system is changing in time. Quantum adiabatic theorem is stating that if this evolution is slow enough, then the system will always stay in the ground state. Then let's check here this h of t. Initially we start with this h mix. So this is our initial Hamiltonian. And we start in the ground state of this h mix at t equals 0. And at t equals 1, at t equals 2, then you can see here that we end up with hc. This is the only Hamiltonian which is acting. So we are gradually introducing hc and removing the impact of h mix. And according to quantum adiabatic theorem, we end up with the ground state of hc at the end of this procedure. Now, how this helps us? Since at the end of the procedure, we end up with the ground state of hc, and this is the lowest energy state of hc, if you can encode your problem through this Hamiltonian so that the lowest energy state of this Hamiltonian corresponds to the optimal solution of your problem, then you can solve your problem using this adiabatic quantum computing framework. Because it's like nature will solve it for you. You prepare the Hamiltonian, you apply some magnetic fields on the qubits, but you need to design this HC in a proper way to encode your problem, so that at the end of this procedure, you end up with the ground state of HC. And quantum annealing is an algorithm running in this framework. What is the difference? Some conditions in adiabatic quantum computing are relaxed. For instance, the system may not be closed. This makes it a heuristic algorithm, meaning that it's not guaranteed that you'll always end up with the optimal solution, ground state. And furthermore, adiabatic quantum computing is equivalent to gate-based computing in the sense that you can do anything in AQC. Anything you can do in AQC, you can do it in gate-based and vice versa. But this is not true for quantum annealing. This is more special to optimization. And this algorithm is implemented by D-wave quantum annealers. And in D-wave quantum annealers, for this H mix, which is the initial Hamiltonian, we have all Pauli X's, and the ground state in that case is the equal superposition state. So this is how we start. And in D-wave, you can apply coupling coefficients to qubit pairs. This is represented by Jij. So this is qubit I, qubit J, and you can apply some coupling constant to qubit pair Jij, and also some magnetic field to qubit I. So this is how the problem Hamiltonian looks like in the case of D-wave machines. For instance, you cannot apply some force to 3 qubits at once. This is not possible. Only like you can apply it to only pairs of qubits. And the ground state of this Hamiltonian corresponds to the minimum energy state of this Ising model. Now, what is this Ising model? Here, SIs are spin variables. They are -1 or 1. So think about this as a function of SIs. You don't know the values of SIs. They can be -1 or 1. But the thing is, if you can express your problem in the form of this Ising model, then you get HI and JIJs. And through this, you construct the problem Hamiltonian, and then you can use quantum annealing to solve your problem. So the question is now, how should I construct this Ising model so that its lowest energy state, so the lowest, this is a function and we want to minimize this function, and we are looking for which SI values minimizes this function. We should design it in a way so that the minimum of this function is the optimal solution of our problem. Now, this is the question. But the thing is, it's not easy to think in terms of spin variables, -1 and 1, but it is often more convenient to work with binary variables, zeros and ones. Now, I will talk about quadratic unconstrained binary optimization. Then we will see how this is really similar to Ising model. I will give a very simple example. Consider this function of two variables, x1 and x2. They are binary variables. And suppose that we would like to minimize this function. For this function, you can view it also as follows. You have like some xi terms, summation of xi terms. In this example, we have 5x1 plus 9x2. And we have some quadratic terms like xi, x2. In this example, we have x1, x2. And to find x1 and x2 that minimizes this function, we can try all possibilities because this is simple. We can try 0, 0, 0, 1, 1, 0, and 1, 1. And from here, it is clear that the pair that minimizes this function is this one. x1 is equal to 0 and x2 is equal to 0. But in general, when your problem is large, this is not an easy task. You cannot try one by one, all possible combinations. So this is why you use different algorithms to solve such problems. So this is, if you check the name, it says quadratic because you have at most quadratic terms. But let me add that there are also higher order models, which allows having terms like xi, xj, xk, or even more. It's binary in the sense that we have binary variables, and it's unconstrained in the sense that this optimization is not subject to any constraints. But we could have something like this. Let's minimize this function such that x1 plus x2 is greater than or equal to 1. In this case, our answer will be different because then our answer cannot be this one, but it is either one of those three. And it would have been this one, x1 equals 1 and x2 equals 0. So this is a constraint problem. Luckily, we can convert constraint problems into unconstrained ones. So this is possible. But Kubo is an unconstrained problem. You just have a quadratic function written in terms of binary variables, and you want to minimize it. Let's see a more concrete example to see how one can formulate real-world problems using this Kubo formulation. Here I will talk about Trebling-Salesman problem. In Trebling-Salesman problem, you are given a list of nodes. You are given a graph representing some cities, and you are given cost between each city, and your goal is to find a route which passes each city exactly once. It's a closed route, and you would like to find the route with the minimum cost. So this is your goal. And so how can we express this problem? Through Kubo formulation. The first thing you do is to define your binary variables. And in this case, we define such binary variables of the form BTI. And BTI is 1 if node I is visited at step T in the tour, and it's 0 otherwise. So for instance, if B10 is equal to 1, this means node 0 is visited at step 1 in the tour. We don't know this beforehand, but we try to express our problem using those binary variables so that we when we minimize this function, we find the correct variable assignment that minimizes the function. And that variable assignment will give us the solution. If after minimizing, we find out that B10 is equal to 1, this will mean that at step 1, we visit node 0, for instance. Let's start with the objective function, because this is more natural and easier to understand. So what is our objective? Is to minimize the cost. And what is the cost? How can we express it through those binary variables? See here we have consecutive time points t and t plus 1. And we have bti and bt plus 1j. So if both of them are equal to 1, this means at time t I am at city I, and at time t plus 1 I am at city j. So I am traversing edge ij. Hence, I am adding the cost of wij. So we are adding those costs, wij's, whenever edge ij is traversed. And this is our objective function to minimize. But this is not enough because we need to have some constraints. For instance, we cannot have such a thing. We cannot have B11 and B12 equals 1 at the same time, because this would mean we are visiting city 1 and city 2 at time 1. This is why we have such a constraint here, saying if you take a summation for a fixed t over different i's, it should be 1. And similarly, you cannot have such a thing like B31 and B51 are both equal to 1, because this would mean you are at city 1 at times 3 and 5. But this is not possible. So this is why we have the second constraint. And for fixed I, if you take a summation over t's, it should be 1. But I mentioned that Kubo is a non-constraint model, so what we will do, we use something called penalty methods. And here how those constraints are incorporated inside the this is how those constraints are incorporated in the objective function. Observe that if the sum is not 1, then here we have a positive number because it's squared. And then we have a positive penalty multiplied by A1. So whenever a constraint is violated, we are increasing our objective function, which we would like to minimize. So this is not something desirable, since we are trying to minimize this function. So overall, when this thing will be minimized, those states in which constraints are violated, they will not be favorable. They will be penalized. So this is the idea behind penalty methods. Now, obtaining your Kubo formulation, as we did, for instance, for TSP, check the similarity between the Ising model and the Kubo formulation. They are really similar, except that instead of binary variables, we have spin variables in the Ising model. So what we do is, through this variable change, by replacing binary variables with their spin equivalents, we obtain the equivalent Ising model. So that the variable assignment that is minimizing this Kubo formulation corresponds to some spin assignments minimizing this Ising model. And this is how we obtain those HI and JIJs. And finally, we can now use quantum annealing to find a variable assignment that minimizes the energy. And this means we will end up with some things like, okay, SI is equal to 1, SJ is equal to 0, and so on. And this is actually encoding our solution. What are some advantages and disadvantages of quantum annealing? So one advantage is currently we have larger number of qubits compared to gate-based models. D-Wave's latest quantum annealer has around 5,000 qubits. So this is an advantage compared to gate-based model. You can try larger things. And another advantage is that it's aiming at optimization problems, which really have real-world applications, which makes it interesting for especially companies. I think this is why it is so popular. So both qubit size and this real-world application. But what are some disadvantages? One of them is embedding problem. Consider that you have the following QUBO: x1, x2 plus x2, x3 plus x3 plus x1. So we have 3 qubits, and all those 3 qubits should be connected because we have a coupling coefficient for x1, x2, for x2, x3, and for x1, x3. However, in the hardware of D-Wave, there are no such 3 qubits which are connected together. So the solution is embedding. And for instance, in the real machine, one logical qubit is represented by 2 physical qubits. So they are, for instance, both representing x1. They are both 1 at the same time and 0 at the same time. This is called a chain. This is, first of all, increasing the number of physical qubits required. Secondly, the longer your chain, the worse solutions you get. So this is another problem. So this is one of the disadvantages. Another thing is if you run your problem on D-Wave, for large instances, you see that you don't get the optimal solution. This is probably due to noise. And error correction on D-Wave machines is not really evident. This is another disadvantage I can say. But what I have been doing about quantum annealing, I have been modeling some problems, finding some QUBO formulation for those problems, and running some experiments on D-Wave to see what's coming out, basically. Let me start with showing salesman problem with time windows. I will briefly describe each problem without going into detail. Here on top of TSP, you have also time window constraints, which is stating that you should visit the city within this time frame, after the starting time and before this ending time. If you arrive early, then you need to wait, but you cannot arrive later than its latest start time. And this is like making the problem more complicated. There was a QUBO formulation for this problem, but it had a flaw. So what we did was we fixed this flaw and we presented 2 other QUBO formulations for this problem. And we ran some experiments on D-Wave machines. However, the results were not really promising, I should say. Now this is completely different. Here we have music generation. And what's the goal? The goal is to generate a melodic sequence of pitches, which is plausible to the ear. But the thing is, how can we formulate this as an optimization process so that then we can use quantum annealing? You may say, what makes it special to use quantum annealing? Actually, of course, one can solve this using some classical optimization algorithm as well. But also quantum annealing provides some noise, which makes the solutions more interesting. You don't always get the optimal solution, but you have some quantum noise introduced as well. And it's not really common to study music generation as an optimization problem, I should say. This started as a clean turn research project on the QWorld. And you can find it on arXiv. We also have a Jupyter notebook, which you can follow. And this will be published as a chapter in this book, Quantum Computer Music, Foundations, Methods, and Advanced Concepts, edited by Professor Eduardo Miranda. This will be published, I think, at the end of October. And again, a music-related problem. Here we are given a music piece with, let's say, T tracks, but we want to reduce it to a music with M tracks, where M is less than T. So suppose you have some orchestral music, but you would like to arrange it for 2 instruments, but in a way that you would like to capture the essence of the music as much as possible. And actually, it turned out that this is related to a job assignment problem, where there are some jobs, there are some machines, and you would like to assign jobs to machines. For this problem, we came up again with a Cuba formulation. This is still ongoing work. So we came up with a Cuba formulation where we wanted to minimize while we maximize the amount of information contained in the music piece. We tried to minimize the gaps as much as possible. So when you listen to it, you don't hear gaps in the music. This is another project we worked on last year. BMW initiated a quantum computing challenge where they proposed some use cases, and this was one of them. Whenever a company is producing a car with new features, they need to test those features. And for this, they need to build test cars. But this is something costly. Therefore, they need to produce test cars as few as possible. But those test cars should obey some conditions. For instance, there can be a test requiring a car with feature A, with feature B, but not with feature C, etc. And furthermore, there are some configuration rules saying that, for instance, if the car is of type 1, then it should contain feature A, B, but not C. Or if it contains feature A and C, it should contain also feature D. So there are lots of rules which should be satisfied. Meanwhile, we need to minimize the number of cars required for those tests. So this was the problem. And for this problem, we considered D-Wave's hybrid constrained quantum annealer, which was introduced, I think, last year in autumn. In this solver, you don't need to come up with a Cuba formulation. You can directly express your problem together with some quadratic constraints and with a quadratic optimization function. We benchmarked the results with classical optimizers. Actually, the results were really similar. Classical solvers performed slightly better, but it was really slightly better. However, they were faster, I should say. But still, this hybrid constraint solver was promising for future in the sense that we got something comparable to a classical solver. One drawback is that the internal working of this hybrid constraint solver is not revealed. So you don't know which part is solved on classical and which part is solved on quantum. So this is kind of a question. But anyways, this is also available on arXiv. And finally, I worked on this railway dispatching problem. Here we have a railway network, and our goal is to reduce the delays by taking some rerouting and rescheduling decisions. And again, we have some constraints. For instance, like the minimum distance between 2 trains, or minimum stay of the train on a station, whether there are there should be a single train on the track, or there can be double, etc. Again, like we propose some Cubo and higher order model formulations for this problem, and we solve them using D-Wave's hybrid solver. And this was about quantum annealing. And at the beginning of my talk, I mentioned that there were two main approaches. Now I would like to talk about the second one, which is quantum approximate optimization algorithm. This is for the gate-based model, but it can be viewed as a tractorization of HUC. Again, we have HMix and HC, but this time we apply them like HMix, HC, HMix, HC interchangeably. And we have some parameters here, beta and gamma. So we start with some initial state. And in this conventional QA, this is eco-superposition state. And as for the mixer, we select like pole X gates on each qubit. And then those parameters, so we apply those for P layers. We call each of those green boxes a layer. So therefore, in total, we have two P parameters. We start with some initial parameters. We construct the circuit, we measure it, and then this expectation you see is approximated through this measurement, and a classical optimization algorithm is used to maximize this expectation, and those variational parameters are optimized. So we obtain a new set of variational parameters. So this is how QAOA works. It is a hybrid algorithm in the sense that we have classical optimization of the parameters, and we have a quantum circuit. As I mentioned, this is for gate-based model, unlike adiabatic quantum computing, but it's inspired by adiabatic quantum computing. And a generalization of this is quantum alternating operator ansatz. Here, instead of eco-superposition, you may start in any state, but to solve your optimization problem, what you do is you start in a subspace of the full Hilbert space containing all the feasible states. And you should select an H mix so that it preserves the space, meaning that it maps feasible states to feasible and unfeasible to unfeasible. As an example, you may start in eco-superposition of one-hot states instead of eco-superposition of all states. One-hot means there is only one in the state, so like 100010001. And this X5 mixer you see, it preserves the space of one-hot states. Let me show you this through an example. On the left-hand side, you'll see the QBA formulation for TSP we have considered. And suppose we have three cities labeled 0, 1, 2. This means we will have 9 qubits representing the variables B00, B01, B02. So this is like T equals 0, the first one. You can think of each one of those as a register. We have T equals 1 and we have T equals 2. And in the when you do conventional QA with this QBA formulation, you start an eco-superposition of all possible states in each register. And you apply this QBA formulation. But for instance, you cannot have such a state like 0, 0, 0, because this means B00 is 0, B01 is 0, and B02 is 0. But we know that exactly one of those bits should be set to 1, because at T equals 0, we should be visiting some city actually. On the right-hand side, you see the case where we are starting in eco-superposition of one-hot states. And 100 means we are in city 1, city 0, sorry. And 010 means we are in city 1, and 001 means we are in city 2. Because 100 means B00 is set to 1, and the other 2 bits are set to 0. And as you see, right now we don't need one of the constraints. It is already satisfied. And you see the new Cuba formulation we obtained. We removed one of the penalties. Because the states are already in equal superposition of only one hot states. And we don't have invalid states like 0, 0, 0, 0, 1, 1, or 1, 1, 1. However, we still need the penalty, uh, other penalty term, because we don't want something like this. We don't want 100 both in the first and the second registers. This would mean first city is visited at time t equals 0 and also at time t equals 1. In actually in TSP, the feasible states form a permutation, meaning that each city should appear at each place exactly once. But this is another detail. But this is the advantage of quantum alternating operator ansatz. Your evolution takes space in a smaller space, and as a result, your Cuba formulation is using less number of terms. No, a study we initiated on this is about error mitigation through mid-circuit measurements. Suppose that, as in the example I showed you, we start in one hot state. This means that if there is no noise throughout the computation, we will stay within those one hot states. We will never have something like 0, 1, 1. And the idea is if you can detect and remove such unvalid states during the evolution, then you can mitigate the error. So this is the main idea. And this detection is done through mid-circuit measurements, meaning in the middle of the circuit, you are performing some measurements. You can do this by filtering, meaning that you have some ancilla states, which are initially in all the qubits are in state 0, and you're applying some unitary. And for instance, in the case of one hot state, you check if all the states are one hot. If not, alpha is no longer in all 0 states, and you detect this. For k-hot states, you can do this by counting the number of ones and checking if it is equal to k or not. You are doing this through a quantum circuit, by the way. For instance, there is something called binary encoding, where you encode everything in binary. For instance, you can encode cities in binary so that 0, 0 is city 0, 0, 1 is city 1, 1, 0 is city 2, etc. And if there are only 3 cities, this means 1, 1 is not a valid state. So you can detect this and remove this. And another idea is post-selection by compression. Here, this applies for binary encoding and one-hot states. So there is a conversion circuit which converts one-hot states to binary. You apply this conversion circuit, and at the end of this procedure, you expect some bits to be in 0 state if your initial state is a one-hot state. So you measure those qubits. If they are not all 0, this means the state is not a one-hot state. So there is an error and you can remove this. Now, finally, I want to talk about our recent work, which I'm really excited about. Here, we are designing near-optimal circuits for QAA. So we introduced an alternative way for implementation. And through this, we were able to obtain near-optimal cosmetics for problems like TSP and max-k-cut, sorry. And what is an optimal cost metric? So, for instance, number of qubits, number of gates, depth of the circuit, and for those cost metrics, we were able to obtain near optimal values. Now, what's the state of the art? You start with a QUBO or HOBO. You get the corresponding Ising model, as in quantum annealing. Then you implement each term in the expression one by one. So this is the state of the art. Our idea is instead, don't get Cubo or Hobo. By the way, Hobo means higher order. Instead, start the classical pseudocode function and implement this using a quantum circuit. I know this is not clear right now, but it will be clear when I give the example. Now, how to implement QA? If you look at it in more detail, first you start with a Cubo formulation. Here we have 2xi xj minus xi minus xj. This is actually Cubo formulation for Qiskit problem, which is defined on graphs. I won't go into detail. Then you obtain the corresponding Ising model by making this replacement, by replacing xi by 1 minus si over 2. And this is what we end up with. Since 1 over 2 is a constant, and also this minus 1, it will be a constant, you can remove those. So we have minimized SI-SJ pairs, where ij's are coming from the, where ij is an edge of the graph, let's say. And the corresponding Hamiltonian is ZIZJ, product of ZIZJ, like ZZ interaction. And how we implement this Hamiltonian? This is the corresponding unitary, UHP, as you see here. And after totalization, this is the circuit you get. So for this Z0, Z1 interaction, this is how we implement this. So the C naught, RZ, and C naught. And for this Z1, Z2, this is here. For Z0, Z3, it is here, and so on. So you implement this term-wise. This is the main idea. Let's see another example. Consider this binary optimization problem. This is product of BIs. BIs are in binary. So suppose that you want to minimize this function. So again, you obtain the equivalent Ising model, which looks like this. But now the problem is, this Ising model has exponential number of terms. Because think about what will happen if you multiply n many 1 minus si's together. This will result in exponentially many terms. And the best circuit you can find for this is this one. This is even not a naive one, but an optimized one. However, this contains exponentially many C0 gates, which is totally not desirable, having lots of gates. However, the circuit you see below is also performing the same thing. Actually, the ground state of those two Hamiltonians, corresponding Hamiltonians, is the same. If you check this problem, if you set all bits to 1, this is when you have the lowest energy, because then it's minus 1. But whenever one of the bits is 0, then it's not, then the energy is 0. So actually, what you can do is, you can check if all bits are set to 1, and if this is the case, in an ancilla, you set your ancilla to state 1, then you perform the rotation, and then you uncompute. So there's an equivalent circuit, but following the conventional way, we end up with a circuit which is requiring more resources. So this is what inspired us. Instead of using the conventional approach, can we directly start with the problem, a classical pseudocode for solving this problem? This looks also similar to Grover's search, actually the oracle part, because think about the oracle. You check if you have some, if your state is satisfying some property, then you mark it. So it's kind of similar, as you will see. We call this approach find QA, and this is our claim, as I mentioned. And we were able to show this for TSP and Max K-cut. Now I will show it for TSP. Here in this table, you see some state-of-the-art solutions and our solution. And for instance, you can see the optimal number of qubits is n log n, and we could achieve this. Optimal number of gates is n squared. And so far, no method was able to achieve this, and we achieved this. And depth, optimal depth was n, and we were able to achieve n log n. So in all cost metrics, we were able to achieve near optimal values. And how do we do this? Instead of the conventional Cuba formulation, we think it in the following way. So we have the cost part, and we also have that the input state should be a permutation. We use binary encoding, meaning that cities are represented like 000110 in binary. But now, how to check if they're forming a permutation? We don't use the penalty method, but this is what we use instead. So think about a classical algorithm. Suppose that I give you a list of 10s. So say we have 10s corresponding to different registers, and I ask you to check if this is forming a permutation or not. The easiest solution that comes into mind is to count the occurrence of each city. If each city is appearing exactly once, then this is a permutation. Otherwise, it's not a permutation. For instance, if it is like 1023, then it's a permutation. But if it is 1012, then it's not a permutation because one is appearing twice. So basically, this is the idea. We check if the state is forming a permutation or not. And if not, we set some flag qubit to 1, and we penalize this through this RZ rotation, and we uncompute. But note that this checking if the state is forming a permutation or not, this is done quantumly through a quantum circuit. So we count the occurrence of each city modulo 2 using a quantum circuit. And as our starting point, we have this classical pseudocode you see on the screen, which is kind of mixture of quantum and classical, but it's inspired by classical idea of counting the occurrence of each city. And for the cost of the root, if you follow the conventional Cubo encoding, note that we are encoding the visited city at each time point, meaning that at time 1, I am visiting this city. At time 2, I am visiting this city, and so on. And if you do this, to incorporate the cost, we need to consider all time pairs like TT plus 1. And for each time pair, you need to consider all city pairs, like all city pairs ij. So there are n square such city pairs, and there are n time pairs, and overall we have n cubed. And this means you need to incorporate n cubed gates. However, there's another encoding called like city-to-city representation. And in this one instead, you're encoding which city to visit next. Say in first register, we are encoding which city to visit after first city. In the second register, we are encoding which city to visit after second city, and so on. And through this, when you check the first register, you already know that you are going out from the first register, and there are only n possibilities to consider. And there are n of those, and you end up with n squared gates instead. You may ask, then why don't we start with this initially? But it is really hard to check if it is performing a permutation or not. So what we do instead is we make a conversion between the two encodings, we compute the cost, and we go back. So this is mainly our idea. And we were able to apply this idea to TSP as well as to max K-cut. You can check the details on arXiv. This is also available on arXiv. And this is the end of my presentation. I will be happy to answer any questions you have.
Thank you so much. That was an awesome talk. Yeah, thank you for sharing your journey and about Q World and presenting your research in such an accessible manner. Uh,
Thank
if
you.
you have any questions, please feel free to drop them in the chat box. We'll have a Q&A session shortly. But before I read the questions, I have a brief announcement for those of you who are participants of our Quantum Explorers program. The password of the Eminent Scientist badge is experiment with a capital E followed by the percentage sign. So we will drop that in the chat box too. And for those of you who are watching the recording, the password is in the closed captions. And yeah, so please feel free to start dropping your questions in the chat box. And while we wait for those to come in, um, I can yeah, if those for those of you who are wondering what Quantum Explorers is, it's Qiskit's self-paced gamified quantum computing learning program that we're running until February 2023. And that is okay, so here's one. Where can we find out more information about the quantum music book being released later this month?
Um, if you search in Google the name of the book, I think you will be able to find. Let me type the editor's name. I think you can see it. I may also share my presentation. You can also check so you can also check my archive account, and there we have the preprint of our chapter. And I can also share the presentation where you can find the name of the book as well.
Okay, thank you. So we will add the link to the presentation in the blog, the Quantum Women Invited Talk blog, as well as the recording of this talk. It will be available soon after this event. So no more questions. Don't feel shy. Please feel free to ask Dr. Salehi anything you want. You can ask about any career, study advice, or about her research. Everyone's saying thank you. So many people are saying thank you for the. Yeah, I think actually it was presented so clearly and in such an accessible way that there aren't that many questions. So, yeah. Um, okay, so yeah, the link of this recording, the link of the recording of this talk will be available on the Running Qiskit blog at the permalink, which is qisk.it/quantumwomen. Sorry, qisk.it/q-women. And I will just drop those in the chat as well. We've got a question. I would like to ask if there is any parallel between quantum annealing and simulated annealing.
Thank you for the question. Actually, the name comes from simulated annealing. So for those who don't know simulated annealing, in simulated annealing, again, we are trying to optimize a function. We have some landscape, and we are moving between different points. By point, I mean different variable assignments. We have a temperature value, and at the beginning of the optimization procedure, you can jump between different variable assignments to a larger distance. But as the optimization procedure continues, you decrease the temperature, which allows you to jump only to near positions. So starting with kind of a more global search, you end up with a more local search. There, the driver of the optimizer is the temperature. In quantum annealing, again, we have an energy landscape, and we are looking for the solution that minimizes this function. However, here we are using quantum tunneling to jump between different states instead of this temperature. So this is the main difference. The main driver of this procedure is coming through quantum effects.
Okay, thank you so much. I think that answers the question. If you have any more, I'll wait for about a few more seconds, so feel free to drop the questions. There's one more coming in.
Yeah, sure.
Um, I think they're typing. And if anyone is shy about publicly posting a question, please feel free to message me privately and I will read it aloud anonymously as well. So we've got more thank yous. Okay, here it is. We are actually using QAOA for a reliability optimization, but our results are quite worse when compared to classical results. Is this expected?
Are you talking about real quantum computers or simulators? So if you are talking about real quantum computers, this is really expected.
Simulate. Yes.
Simulators, okay. For simulator, so again, like this is designed actually for quantum computers to work on, but we are running it on a simulator. This may be one of the things affecting the solutions, because we are trying to simulate something which is a quantum system. So we are trying to simulate something which is designed for quantum computers, and our resources may not be that enough for simulating this QoA. So in that sense, I would say this is expected.
All right. Thank you. So I think that's all we have time for now. I thank you once again, Dr. Salehi, for your time and your wonderful talk. And thank you to the audience for joining us today. We hope that all of you will join us for future talks in this series to become inspired for your own quantum journeys. So please do save the Quantum Women Invited Talks page for future talk information and keep an eye out on Qiskit and IBM Quantum socials for future talk announcements. And for those of you who are in Quantum Explorers, you can also find talk announcements in our Discord server. All right. Well, everyone have a great day and night wherever you are, and we'll hopefully see you next time. Goodbye, everyone.
Bye.